Welcome to The Explainer. We're jumping straight into what is, without a doubt, the ultimate cosmic missing persons case today, the hunt for dark matter. We're going to sift through the clues, review the prime suspects, and look at the absolute extremes scientists are going to just to catch this invisible culprit that literally shapes our universe.
But to really get the scale of this mystery, take a second and look around you. The screen you're watching, the chair you're sitting in, the ground outside, the stars in the sky. Everything you can see, touch, and interact with across the entire cosmos, it makes up just a measly 5% of the universe. That is it, just 5%.
So, if we map out the whole shebang, the true scale of the unknown is staggering. About 68% is this repulsive force we call dark energy, and 27% is a completely invisible substance called dark matter. It doesn't emit light, it doesn't block light, we literally can't feel it, and yet it outweighs normal, ordinary matter by more than 5 to 1.
So you might be wondering, how do we even know this stuff exists? Well, the detective work actually kicked off back in 1933. Astronomer Fritz Zwicky was looking at clusters of galaxies and realized they were moving way too fast. If only the visible matter was holding them together, they should have just flown apart. But the case was really blown wide open in the 1970s by Vera Rubin. She found the exact same anomaly with individual galaxies. The outer edges were spinning way too fast to be held in by the gravity of the stars we could see. There just had to be some invisible, massive scaffold holding everything in place.
Section 1. Meet the suspects, primary candidates. Let's look at the lineup and figure out what might make up this invisible mass.
What's wild here is the sheer range of possibilities. I mean, look at this. On the far left, you've got ultralight particles, incredibly tiny, a fraction of an electron volt. And on the far right, massive objects, like giant primordial black holes that could be tens of times heavier than our sun. Physicists have to search across this entire, staggering mass range.
But let's start with our heavy hitter, the WIMP. That stands for Weakly Interacting Massive Particle. For a long time, WIMPs have been the absolute favorite candidate for what we call cold dark matter. In theory, they're perfect. They're heavy bruisers. They move slowly enough to clump together and form the backbone of galaxies, but they rarely ever bump into normal atoms. They only interact through gravity and the weak nuclear force.
Then we have our second main suspect, the axion. If WIMPs are the heavy bruisers, axions are the ultra-lightweight phantoms. Believe it or not, they weren't even invented to explain dark matter. Physicists proposed them to fix a totally different puzzle about why the universe has more matter than antimatter. But it turns out these ultralight particles have a quirk we might be able to exploit. Scientists think axions might secretly pop into tiny flashes of light, photons, under exactly the right magnetic conditions.
Section 2. Stakeout 1. Catching WIMPs. Let's talk about how we actually set traps for these things.
Catching a WIMP is incredibly difficult because they barely interact with us. Plus, the surface of the Earth is constantly getting bombarded by noisy cosmic rays that trigger false alarms. So we have to go deep underground. Shielded inside a mountain or a deep mine, scientists wait for 3 very specific signals: heat, charge, or light. Basically, we're waiting for a WIMP to accidentally rear-end an atomic nucleus in our detector, creating a microscopic vibration, a tiny spark, or a tiny flash of light.
To catch those ridiculously rare collisions, we're running massive global stakeouts. Teams at Xenon NT in Italy and Lux Zeppelin in the US are using multi-ton, super-cooled vats of liquid xenon. Xenon is dense, which makes it a fantastic target. Meanwhile, over in Switzerland at the Large Hadron Collider, they're taking the completely different route, trying to literally smash particles together at near light speed to create WIMPs from scratch, looking for missing energy in the aftermath.
Section 3. Stakeout 2. Luring axions. Now this requires a totally different kind of detective work.
Since axions are so incredibly light, a giant tank of xenon won't do anything. We have to lure them out. Physicists use devices called haloscopes, like the ADMX experiment. They create a massive magnetic field inside a supercooled microwave cavity, hoping to coax a local axion into popping into a detectable photon. On the flip side, we have helioscopes. These literally aim giant magnets straight at the blazing core of the sun, hoping to catch axions that might be continuously streaming out of it towards Earth.
Section 4. Hidden candidates, other possibilities. Our cosmic missing persons case wouldn't be complete with a few wild cards.
So what if it's not a WIMP or an axion? Well, it could be a sterile neutrino. Normal neutrinos just move too fast to clump into galaxies. They're what we call hot dark matter.
But a heavier, specialized, sterile neutrino could be the culprit, and observatories down in Antarctica like IceCube are keeping an eye out. Or, on the completely opposite end of the spectrum, primordial black holes. These are ancient, dense pockets of matter that collapsed into black holes right after the Big Bang. We actually hunt for those using gravitational waves with LIGO.
Section 5. Closing in on the truth. So, after all this, where does the investigation stand?
After decades of building massive underground tanks and aiming giant magnets at the sky, honestly, we haven't found a confirmed signal yet, but we are constantly refining our methods. We're continually contrasting the brute force underground collisions for WIMPs with the highly delicate magnetic photon lures for axions. We are pushing our technology to the absolute limits of sensitivity.
And that brings up a really vital concept. In physics, ruling something out is just as important as finding it. Every time one of these huge experiments announces they found absolutely nothing, it's actually a massive success. It means they've crossed a hiding spot off the map. They shrink the search area and tell the rest of the science world exactly where to look next.
Because of that, the net is finally closing. We've got next-gen detectors coming online that are just mind-blowing. The XLZD consortium is scaling up to a staggering 60 tons of liquid xenon. Argo is looking at 400 tons of liquid argon. We're incorporating revolutionary quantum sensing tech to filter out background noise down to the subatomic level. We are literally hitting a point called the neutrino fog, where our detectors will be so sensitive they pick up normal solar neutrinos as an annoying background noise.
Which leaves us with this final thrilling thought to ponder. The math says it's there. The spin of the galaxies absolutely proves it's there. If 27% of the universe is passing right through us, right through your body at this very second, with all these incredible new tools firing up, how long is it going to take until we finally catch it? Thanks for joining me on this explainer, and keep your eyes on the stars.